There's something undeniably humbling about gazing up at the night sky, realizing that every star, every distant galaxy, represents a question humanity hasn't yet answered. The universe is vast beyond comprehension, and yet with every passing year, we uncover fragments of its secrets that challenge everything we thought we knew. Just when we believe we've mapped the edges of understanding, space throws us a curveball, a discovery so extraordinary it forces us to rewrite the textbooks. And right now, we're living through one of the most explosive eras of cosmic revelation in history. Think about this. In the last few years alone, telescopes have glimpsed black holes behaving in ways that defy physics as we know them. Rogue planets drift untethered between stars, hinting at unseen forces shaping the cosmos. Strange signals pulse from the depths of space, their origins still a mystery. These aren't just incremental updates to science, they're paradigm shifts, clues that could unravel the very fabric of reality. And today, we're diving into 30 of these groundbreaking discoveries, each with the potential to reshape not just astronomy, but our place in the universe itself. Some of these findings sound like they're ripped straight from science fiction, ancient galaxies too mature to exist so early in cosmic time. Planets with conditions that blur the line between impossible and habitable, even whispers of phenomena that might upend Einstein's theories. What ties them all together is their sheer unpredictability. They prove that the universe is far stranger, far more dynamic than we ever imagined. And if history has taught us anything, it's that every great leap in human knowledge starts with a single, baffling observation. So buckle up, because by the end of this journey, you'll see the cosmos in a way you never have before. The first clue that Oumuamua was unlike anything we'd seen before came in October 2017, when astronomers spotted a faint speck of light streaking through our solar system at blistering speeds. At first glance, it seemed like just another asteroid until the math didn't add up. This wasn't some rock from our cosmic neighborhood. Its trajectory revealed an impossible truth. Oumuamua came from beyond our solar system, the first confirmed visitor from interstellar space. But the surprises didn't stop there. Observations showed this mysterious traveler wasn't just passing through, it was behaving strangely. Unlike typical comets, it lacked a visible tail of gas and dust, yet it accelerated as if something were pushing it. Its shape, too, defied logic, long and narrow, like a cosmic cigar tumbling end over end. Scientists scrambled for explanations. Could outgassing hidden vents spewing material account for its speed? Or was something else at play? The more we studied it, the weirder it became. Some researchers even floated a radical idea. What if Oumuamua wasn't natural at all? The possibility of artificial origins sparked fierce debate. Could it be a piece of alien technology, a solar sail catching interstellar winds, or a derelict probe from a distant civilization? While most scientists lean toward natural explanations, the mere fact that the question was taken seriously speaks volumes. Oumuamua forced us to confront how little we know about what might be lurking between the stars. If objects like this are sailing through space undetected, how many others have we missed? This discovery didn't just rewrite the rules, it tore up the rulebook. For decades, we've assumed interstellar visitors would be rare, but Oumuamua's existence suggests they might be shockingly common. Later, a second interstellar object, Borisov, was spotted, this time clearly a comet, proving the first wasn't a fluke. Now, projects like the Vera Rubin Observatory are gearing up to scan the skies for more, raising tantalizing questions. Are these objects cosmic drifters, or could some be deliberate messengers? Either way, Oumuamua taught us one thing: the universe is far stranger and far more active than we ever dreamed. If Oumuamua made us question what drifts between the stars, Venus just threw us an even bigger curveball, one hidden in its toxic, crushing atmosphere. In 2020, astronomers dropped a bombshell. They detected traces of phosphine, a stinky, flammable gas floating in the planet's clouds. On Earth, this substance has one glaringly obvious source: life. Anaerobic microbes produce it in oxygen-free environments like swamps and animal guts. So when telescopes spotted it 40 miles above Venus's surface, where temperatures are oddly Earth-like, the implication was staggering. Could this be our first tangible hint of life beyond Earth? The discovery ignited instant controversy. Venus is a hellscape, its surface hot enough to melt lead, bathed in sulfuric acid rains with atmospheric pressures 90 times heavier than Earth. Yet the phosphine signature, picked up by the James Clerk Maxwell telescope in Hawaii and later confirmed by the Atacama Large Millimeter Array in Chile, seemed unmistakable. Team leader Jane Greaves and her colleagues ran through every non-biological explanation they could think of: volcanic eruptions, lightning strikes, even meteorite dust. None came close to producing the gas in such quantities. The numbers simply didn't add up unless something or someone was actively making it, critics pounced. Some argued the signal was a false alarm, perhaps misidentified sulfur dioxide. Others calculated that unknown geochemical processes, unique to Venus's extreme environment, might spawn phosphine without life. But the biggest hurdle remained: how could anything survive in droplets of sulfuric acid? Then came the counterarguments. Extremophiles on Earth thrive in equally hostile places: boiling hydrothermal vents, nuclear reactor runoff, even inside rocks. If microbes floated high in Venus's atmosphere, shielded from the worst heat and pressure below, they might just eke out an existence. The debate still rages, but one thing's certain: this discovery shattered decades of assumptions. Mars monopolized the search for nearby life, while Venus was written off as a dead end. Now, missions like NASA Da Vinci and Veritas, along with ESA's Envision, are racing to revisit our neglected neighbor. Even private initiatives have joined the hunt, with Rocket Labs planning a phosphine-sniffing probe. Whether the answer turns out to be microbes or some exotic chemistry, Venus just taught us a vital lesson: life, if it's out there, won't play by our rules. The universe doesn't care what we think is possible, it only cares what is. And right now, Venus is whispering secrets we're only beginning to decode. For centuries, the Moon was considered a barren wasteland, bone dry, airless, and utterly incapable of harboring water. That assumption was turned on its head in 2020, when NASA's SOFIA mission made an astonishing announcement. They'd detected water molecules clinging to the sunlit surface of the Moon. Not buried in shadowed craters, not trapped in ice at the poles, but right out in the open where sunlight beats down unfiltered. This wasn't just a scientific curiosity. It was a revelation that rewrote our understanding of Earth's closest neighbor and opened doors to humanity's future in space. The discovery came from an unlikely tool: a modified Boeing 747 jetliner equipped with a powerful infrared telescope. Flying high above Earth's moisture-laden atmosphere, SOFIA instruments picked up the telltale signature of H2O, water embedded in the lunar soil. What made this so baffling was the environment. Without an atmosphere to shield it, the Moon's sunlit surface bakes at temperatures reaching 260 degrees Fahrenheit during the day, hot enough to vaporize water instantly. So how could any moisture possibly survive? Scientists soon uncovered the answer. The water wasn't pooled in liquid form but locked inside microscopic glass beads forged by meteorite impact. These tiny protective shells shielded the molecules from the brutal conditions, preserving them like cosmic time capsules. The implications are staggering. Water is the lifeblood of space exploration, not just for drinking, but for growing food, producing oxygen, and even creating rocket fuel through hydrolysis. Until now, planners assumed lunar bases would need to rely on ice mined from permanently shadowed polar craters, where temperatures plunged to -400 degrees. But if extractable water exists across the Moon's sunlit regions, suddenly the logistics of sustained human presence become far simpler. Imagine astronauts landing near the equator, where sunlight powers solar panels around the clock, and still having access to this critical resource. Yet mysteries remain. Scientists still don't know exactly how much water is trapped in these beads, or how easy it will be to extract. Some theories suggest solar wind could be delivering hydrogen that binds with oxygen in the soil, creating water molecules over time. Others speculate the moon might be harboring far more water than we've detected, hidden in pockets we haven't yet discovered. Missions like NASA's Viper rover, set to map lunar water ice in 2024, will be crucial in solving these riddles. What's clear is this: the moon is far from the desiccated world we once thought. It's a dynamic place with secrets still waiting to be uncovered. And as humanity sets its sights on returning to the lunar surface, not just to visit but to stay, this discovery might be the key that unlocks the solar system. Suddenly, the moon isn't just a destination. It could be the stepping stone that makes Mars and beyond possible. Some of the universe's most baffling signals aren't flashes of light or gravitational waves. They're bursts of radio energy so intense they outshine entire galaxies in a fraction of a second. Fast radio bursts, or FRB, were first detected in 2007, appearing as blips so brief and random. Astronomers initially dismissed them as telescope glitches. But then, in 2016, everything changed. Researchers stumbled upon something unprecedented, an FRB that didn't just flash once. It repeated, and not in a predictable rhythm, but in erratic, enigmatic pulses, as if the cosmos itself were tapping out a coded message we couldn't decipher. The discovery sent shockwaves through astrophysics. Most cosmic explosions, like supernova or neutron star collisions, are one-off events destroying their sources in the process. But a repeating FRB implied something far stranger. A celestial object capable of generating these immense energies over and over without self-destructing. The leading suspect, magnetized neutron stars with magnetic fields so powerful they warp the very fabric of space around them. In 2020, astronomers caught a smoking gun, an FRB erupting from a known magnetar in our own galaxy, confirming these exotic objects could indeed produce the phenomenon. But the plot thickened. While some bursts matched magnetar behavior, others defied explanation, flashing with energies no known process should generate. Then came the real puzzle: what these bursts reveal about the universe's hidden scaffolding. As FRBs race across cosmic distances, they interact with the sparse atoms floating between galaxies, slowing ever so slightly. By measuring this delay, scientists realized they could use FRBs as probes to map the universe's missing matter. The diffuse gas and plasma that's too faint to see directly, yet makes up half the universe's expected mass. It's like turning the bursts into cosmic tape measures, uncovering invisible structures woven through the void. Yet for every answer, new questions emerge. Why do some FRBs repeat while others vanish? Could some originate from advanced civilizations, as a handful of theorists speculate? And why do certain bursts exhibit bizarre substructures, microsecond spikes within spikes, hinting at physics we haven't yet imagined? Projects like the CHIME telescope in Canada are now cataloging thousands of these bursts, hunting for patterns that might crack the code. Whatever their source, FRBs have already proven one thing: the universe is shouting at us in a language we're only beginning to understand. And with every pulse, it offers another clue, not just about distant stars, but about the invisible threads binding the cosmos together. Deep in the constellation Leo, a planet unlike any other in our cosmic catalog orbits a dim red dwarf star, K2-18b. At first glance, it fits the mold of countless other exoplanets, roughly 8.6 times Earth's mass, with a year lasting just 33 days. But when the James Webb Space Telescope turned its gaze toward this distant world, it revealed something extraordinary, a tantalizing cocktail of conditions that could rewrite the playbook on where life might thrive. K2-18b isn't just another rocky sphere or gas giant. It's what scientists call a Hycean planet, a water world shrouded in a thick, hydrogen-rich atmosphere, where global oceans might stretch from pole to pole beneath swirling, steamy skies. The very idea of Hycean worlds is revolutionary. Until recently, the hunt for habitable planets focused on finding Earth-twin places with rocky surfaces, temperate climates, and atmospheres rich in nitrogen and oxygen. But K2-18b challenges that narrow view. Here, the hydrogen envelope acts like a cosmic pressure cooker, trapping heat so efficiently that even far from its star, the planet could maintain liquid water, not in scattered lakes but in planet-spanning depths. Add to that JWST detection of carbon dioxide and methane in its atmosphere, and suddenly, the ingredients for life seem alarmingly present. What makes this discovery so electrifying is the possibility of biosignatures, chemical traces that could only exist if life were actively shaping the environment. On Earth, methane is constantly replenished by living organisms. Without them, sunlight would break it down in mere centuries. So when JWST spotted the gas on K2-18b alongside dimethyl sulfide, a compound produced almost exclusively by marine microbes, here scientists' pulses quickened. Could these molecules be the first whiff of alien biology, or are they just byproducts of unknown geological processes? The answer might lie in the planet's thermal profile. Unlike Earth's atmosphere, where temperature drops with altitude, Hycean worlds flip the script. Their hydrogen blankets create an inversion layer, warming the upper air while the ocean surface stays cooler, a counterintuitive setup that might actually protect aquatic life from lethal stellar flares. Red dwarfs like K2-18b's star are notoriously volatile, bombarding their planets with radiation. But JWST data suggests the atmosphere here is dense enough to act as a radiation shield, while the ocean beneath could serve as a second buffer. Picture a planet where organisms don't drift in shallow seas, but cluster near hydrothermal vents in eternal darkness, their existence betrayed only by the gases they release into the sky. The next steps are clear. JWST upcoming deep spectroscopy studies will hunt for more molecules, especially ammonia, which could hint at nitrogen-based metabolism, or phosphine, that controversial Venusian clue. But the real breakthrough might come from studying chemical imbalances. On Earth, oxygen and methane coexist only because life constantly produces them. Without biology, they'd react and vanish. If K2-18b shows similar contradictions, the case for life grows stronger. Of course, skeptics caution that exotic chemistry could mimic biosignatures. Hydrogen-rich atmospheres are alien labs where reactions unfold in ways we've never seen. One thing's certain, K2-18b has shattered the paradigm of habitability. No longer can we dismiss gas-shrouded worlds as sterile hellscapes. Instead, they might be the universe's most common cradles for life, hidden oases where evolution follows paths we've yet to imagine. And with JWST peeling back the layers of that hazy atmosphere, each observation brings us closer to answering humanity's oldest question: are we alone? Or is the cosmos teeming with neighbors waiting in the depths of alien seas? We picture galaxies as flat, elegant spirals, neat disks of stars spinning like cosmic records. But the Milky Way isn't playing by those rules. In 2019, astronomers made a startling realization. Our galaxy isn't just warped, it's rippling like a tablecloth shaken at its edges. This isn't some subtle bend. Entire sections of the disk twist upward by thousands of light years, while others dip below the plane, creating a sprawling, three-dimensional wave that arcs across the cosmos. And the cause, that's where things get even stranger. This celestial contortion isn't static. The ripples move, propagating outward like vibrations through a drumhead. One leading theory points to our galaxy's messy past, a violent collision with a dwarf galaxy billions of years ago. the Sagittarius dwarf, a tiny neighbor currently being torn apart by the Milky Way's gravity, is the prime suspect. As it repeatedly plunges through our galactic disk, simulations show it could send gravitational shockwaves rippling through the stars, warping their orbits like a stone tossed into a pond. But there's a twist. Some researchers argue the Sagittarius impact alone couldn't account for the scale of the distortions. Enter dark matter, the invisible glue holding galaxies together. If uneven clumps of dark matter lurk in the Milky Way's halo, their gravitational tug could amplify the ripples, turning a minor perturbation into a galactic-scale undulation. This idea flips traditional dark matter models on their head. Instead of a smooth, diffuse cloud enveloping our galaxy, we might be looking at lumpy, dynamic concentrations, structures massive enough to carve visible wrinkles into the fabric of the disk itself. The implications are staggering. If dark matter can sculpt galaxies so dramatically, it suggests our understanding of its distribution and behavior is woefully incomplete. What's more, these ripples aren't just cosmetic, they're rewriting the rules of galactic evolution. Stars born in warped regions follow different trajectories than those in the flat disk, altering how they age, interact, and even seed future generations. Gas clouds, the raw material for new stars, get pushed into unusual configurations, potentially triggering bursts of star formation in unexpected places. Suddenly, the Milky Way isn't a serene, orderly structure. It's a dynamic, ever-changing entity, still bearing the scars of ancient collisions and humming with unseen forces. The discovery also raises a provocative question. If our own galaxy is this misshapen, how many others are we misjudging? Distant galaxies appear flat because we see them edge on. But what if they're just as contorted, their wrinkles hidden by perspective? Upcoming telescopes like the Vera Rubin Observatory could reveal these hidden distortions, forcing us to reconsider the true diversity of galactic shapes. For now, the Milky Way's ripples stand as a humbling reminder. Even our cosmic home still has secrets to spill, and some of them are hiding in plain sight. For decades, black holes have been cosmic paradoxes, regions where gravity crushes matter into an infinitely dense point called a singularity, a place where the laws of physics simply break. But what if singularities don't exist at all? Enter the fuzzball, a radical string theory concept that reimagines black holes not as bottomless pits, but as tangled knots of vibrating strings brimming with structure all the way down. This idea might just solve one of physics' greatest puzzles, the black hole information paradox. The paradox began with Stephen Hawking's groundbreaking work in the 1970s. He showed that black holes aren't truly black, they slowly leak radiation, evaporating over eons. But here's the catch, that radiation carries no information about what fell in. If a black hole vanishes entirely, everything it swallowed, every atom, every particle's quantum state, would be erased from the universe, violating a fundamental law of quantum mechanics. Information must always be preserved. Physicists wrestled with this for decades. Some proposed hidden layers of reality, like holograms storing data on a black hole's surface. Others suggested information might escape via wormholes. But the fuzzball theory offers a cleaner, stranger solution. Imagine a black hole's core not as a dimensionless point, but as a vibrating, frenetic ball of strings, each thread of energy woven so densely it fills the entire event horizon. No singularity, no void, just an ultra-complex tangle where every bit of swallowed matter is encoded in the string's vibrations. When Hawking radiation leaks away, it carries traces of that encoded data, preserving information naturally. The math checks out, but the implications are mind-bending. Fuzzballs would mean black holes aren't the featureless traps we thought. Instead, they're alive with quantum detail, their interiors buzzing with the fingerprints of everything they've consumed. Critics argue that fuzzballs lack observational evidence after all. We can't peek inside a black hole to check, yet subtle clues might exist. Some theorists predict fuzzballs would echo gravitational waves differently than classic black holes during collisions. LIGO, the observatory that first detected these ripples in spacetime, is now hunting for these very echoes. Others suggest fuzzballs could alter the shadow images captured by the Event Horizon Telescope, potentially explaining odd brightness variations in the ring around M87's supermassive black hole. Whether fuzzballs are real or not, their value is undeniable. They force us to rethink the nature of spacetime itself, challenging the idea that gravity inevitably tears reality apart at extremes. Instead, they paint black holes as the ultimate cosmic archivists, not destroyers, but transformers where information is never lost, only rewritten in a language we're just beginning to decipher. And if string theory's wild vision holds, the universe might be far more intricate, far more knowable than we ever dared to dream. In the constellation Aquarius, a dim red dwarf star barely 1/10 the Sun's mass hosts one of the most tantalizing planetary systems ever found, TRAPPIST-1. Discovered in 2017, this ultra-cool dwarf is orbited by 7 Earth-sized worlds, 3 of which sit snugly in the habitable zone, where liquid water could pool on their surfaces. At just 40 light-years away, these planets are close enough for the James Webb Space Telescope to scrutinize their atmospheres, turning what was once speculation into concrete data. But the more we learn about TRAPPIST-1, the clearer it becomes. These aren't just Earth twins. They're laboratories for extreme planetary science, challenging our assumptions about what habitability really means. The first hurdle is tidal locking. Like the Moon to Earth, these planets likely show one face permanently to their star, creating a world split between eternal day and endless night. The day side would bake under relentless heat, while the night side plunges into icy darkness. At first glance, this seems like a death sentence for life, no temperate twilight zone, just extreme gradients of scorch and frost. But nature has a way of surprising us. Atmospheric circulation could redistribute heat, creating a narrow band of habitability along the terminator line, where perpetual sunrise or sunset conditions might exist. Imagine a ribbon of twilight wrapping around the planet, where temperatures hover just right for water to flow, sheltered from the worst stellar flares. Then there's the question of atmospheres. Without a thick blanket of gases, any water on these worlds would either boil away or freeze solid. Early JWST observations have already ruled out hydrogen-dominated atmospheres on 2 of the inner planets, suggesting they're more likely rocky with thin, Venus-like envelopes, or worse, stripped bare by their star's wrath. But the real prize lies with TRAPPIST-1e, F, and G, the middle siblings squarely in the Goldilocks zone. Here, JWST infrared eyes are hunting for molecules like carbon dioxide, ozone, and methane, hints of geological activity or even biology. A detection of oxygen without methane could be especially telling, as it might point to photosynthesis at work. Yet TRAPPIST-1's star complicates everything. Red dwarfs are tempestuous, frequently erupting with radiation bursts that could scour atmospheres clean over time. Some models suggest these planets might have started as water worlds, only to have their oceans boiled off into space, leaving behind desiccated husks. Others argue that magnetic fields or chemical cycles could replenish lost gases, creating a delicate equilibrium. The system's compact layout adds another twist. The planets are so close together. Their gravitational tugs could generate internal heat through flexing crusts, fueling subsurface oceans like those on Jupiter's moon Europa. What makes TRAPPIST-1 revolutionary isn't just the possibility of life, though. It's the sheer diversity of Earth-sized worlds packed into one system, offering a comparative study of how subtle differences, distance, composition, star activity shape planetary destinies. Over the next decade, JWST and future telescopes will peel back the layers of these enigmatic worlds, testing whether they're cautionary tales or proof that life thrives in the unlikeliest corners. Either way, TRAPPIST-1 has already taught us a vital lesson. The universe doesn't do simple. It crafts complexity, then dares us to decipher it. There's an invisible force in the cosmos tugging at our galaxy, and everything around us with the gravitational pull of 100,000 billion suns. Astronomers call it the Great Attractor, and it's one of the most perplexing enigmas in modern astrophysics. This colossal anomaly lies about 250 million light-years away in the direction of the constellations Centaurus and Hydra, dragging the Milky Way and its neighboring galaxies toward it at a staggering 1.4 million miles per hour. But here's the catch: we can't see it. The very thing dictating our galactic motion is hidden behind a cosmic curtain, the Milky Way's dusty, star-choked galactic plane, known as the zone of avoidance. For decades, the Great Attractor was little more than a gravitational shadow, an unexplained deviation in the motion of galaxies first noticed in the 1970s. Telescopes couldn't peer through our own galaxy's bulge to spot what was causing it, leaving astronomers to theorize about unseen superclusters or even exotic dark matter structures. Then came a breakthrough in 2014 when researchers mapped the motions of thousands of galaxies and uncovered the true scale of our cosmic neighborhood. The Great Attractor isn't a lone monster, it's the heart of the Laniakea supercluster, a vast web of galaxies spanning 500 million light-years, with the Milky Way clinging to its filamentary outskirts like a spider on the edge of a web. Yet the mystery only deepens when you consider what's beyond the Great Attractor. Infrared surveys piercing through the zone of avoidance have revealed something even more massive: the Shapley supercluster, a gravitational titan 650 million light-years away, pulling Laniakea and us toward it. This raises a tantalizing question: is the Great Attractor merely a waypoint in a far grander cosmic flow? Some simulations suggest these movements might trace back to the very origins of the universe's ancient density fluctuations from the Big Bang that set entire superclusters in motion like ripples in a pond. The real challenge lies in observation. The zone of avoidance isn't just a visual obstacle, it's a radio quagmire where interstellar gas and dust scramble signals from beyond. New tools like radio telescopes and X-ray observatories are finally cutting through the noise, revealing galaxy clusters lurking behind the murk. One such discovery, the Norma cluster, appears to be a key component of the Great Attractor's mass, though it's still not enough to account for the full gravitational pull. This gap hints at something even more profound: vast reservoirs of dark matter woven through the supercluster like invisible scaffolding, amplifying its influence in ways we're only beginning to measure. What's clear is this: the Great Attractor isn't just pulling galaxies, it's pulling back the veil on how the universe organizes itself on the grandest scales. Every new observation forces us to rethink the balance between visible matter and the dark, unseen forces that shape our cosmic home. And as technology peels away the Milky Way's dusty shroud, we're not just solving a local mystery. We're mapping the gravitational highways of the cosmos, one hidden landmark at a time. Dark energy has long been the universe's most enigmatic puppeteer, an unseen force accelerating the expansion of space itself, stretching galaxies apart faster with each passing moment. For years, scientists assumed its strength was constant, woven into the fabric of cosmology as a fixed number called the cosmological constant. But what if dark energy isn't steady at all? A growing body of evidence suggests it might be changing, fluctuating over cosmic time in ways that could rewrite the destiny of everything. The clues come from painstaking measurements of the universe's expansion rate, using celestial landmarks like supernova and baryon acoustic oscillations, frozen ripples from the early cosmos. When researchers compared these markers across different epochs, they found discrepancies. The universe isn't just speeding up, it might be accelerating unevenly, as if dark energy's push grows stronger or weaker depending on when or where you look. One striking analysis from the Dark Energy Survey even hints at a possible dip in dark energy's influence around 8 billion years ago, followed by a resurgence. If verified, this wouldn't just tweak our models, it would demolish them, suggesting dark energy is dynamic, evolving, and far stranger than Einstein's static concept. The implications are cosmic in scale. If dark energy strengthens over time, it could trigger the Big Rip, a cataclysmic endgame where the force of expansion tears apart galaxies, then stars, then even atoms, reducing all matter to lonely particles drifting in an infinite void. Conversely, if it weakens, gravity might regain dominance, leading to a big crunch where the universe collapses back into a singularity. There's even a third, haunting possibility. Dark energy could oscillate, driving cycles of expansion and contraction that echo theories of a cyclic universe. Now, the Dark Energy Spectroscopic Instrument, DESI, is mapping millions of galaxies with unprecedented precision, hunting for patterns that might confirm these ideas. Early results are already stirring debate. Some data aligns with a slowly weakening dark energy, while other measurements suggest wilder variations. The stakes couldn't be higher. If dark energy isn't constant, then our entire cosmic timeline from the Big Bang to distant fate might need reimagining. What's fascinating is how this ties into quantum physics. Some theorists propose dark energy could be a field akin to the Higgs, one that interacts with itself or other forces in ways we haven't detected. Others speculate it's tied to extra dimensions or even the vacuum energy of empty space itself. Every new DESI observation brings us closer to answers or deeper into the unknown. One thing's certain, dark energy isn't just shaping the universe, it's daring us to question everything we thought was settled about how the cosmos lives, breathes, and ultimately ends. The idea of liquid water on Mars has tantalized scientists for generations. Visions of ancient river valleys and dried-up lake beds fueling dreams of a once blue neighbor. But in 2018, the dream took a radical turn when the European Space Agency's Mars Express orbiter beamed back data revealing something far more immediate. Not just relics of water, but actual lakes hidden deep beneath the ice of the planet's south pole. The discovery sent shockwaves through the scientific community. Buried under a mile of frozen carbon dioxide and water ice, these reservoirs stretched across dozens of kilometers, their presence betrayed by eerily bright radar reflections, the kind only liquid water could produce. Initial excitement quickly collided with skepticism, though. The temperatures at Mars' poles plunged to -200 degrees Fahrenheit, far colder than any known liquid water could naturally exist, even under pressure. How could lakes survive in such extremes? The leading theory pointed to ultra-salty brines. On Earth, bodies like Antarctica's Don Juan Pond remain liquid despite frigid temperatures, thanks to high concentrations of calcium and magnesium salts that act as antifreeze. If similar chemistry existed in these Martian reservoirs, it might explain their persistence, but then came a curveball. Some researchers argued the radar signals could instead be coming from smectite clays, minerals that trap water molecules in their layered structures, mimicking the reflective signature of liquid. The debate rages on, but the stakes are immense. If these are bodies of liquid brine, they'd be the most promising habitats for present-day microbial life beyond Earth. Extreme environments on our own planet, like Antarctica's Blood Falls, where iron-rich brine harbors resilient bacteria, prove life can thrive in seemingly inhospitable conditions. Mars' underground lakes, shielded from deadly surface radiation and possibly warmed by geothermal heat, could offer similar refuges. The challenge lies in reaching them. Drilling through a mile of ice in Mars' thin atmosphere is a monumental engineering feat, though concepts like nuclear-powered cryobots are already in early development. What makes this discovery so paradigm-shifting isn't just the potential for life. It's the realization that Mars might still be geologically alive. The energy required to keep these reservoirs liquid hints at residual heat deep in the planet's core, perhaps from lingering volcanic activity or the decay of radioactive elements. That heat could drive subsurface water circulation, creating dynamic environments where chemical reactions, and maybe even life, persist. Future missions like NASA's planned Mars Life Explorer aim to settle the debate by probing these hidden depths directly. Until then, those enigmatic radar reflections remain a siren call inviting us to uncover whether the red planet's most profound secrets lie not on its surface but beneath it. Most cosmic explosions follow a familiar script. Supernova blaze brightly for weeks, gamma-ray bursts flare in seconds. But in June 2018, astronomers spotted something that defied every expectation. Nicknamed the Cow after its random catalog designation, a T-2018 Cow, this violent flash brightened 30 times faster than a typical supernova, then vanished almost as quickly, leaving behind a mystery that's rewriting our understanding of stellar deaths. Discovered by the Atlas telescope in Hawaii, the Cow erupted in a seemingly quiet galaxy 200 million light-years away. Within 3 days, it shone 10 times brighter than a normal supernova, emitting staggering amounts of high-energy X-rays and radio waves. Most bizarrely, its light curve didn't match anything in the cosmic playbook. No gradual fade, no lingering afterglow. Instead, it peaked explosively, then dropped off a cliff as if someone had flicked a celestial switch. The event was so unusual that astronomers initially suspected an instrument error. Then telescopes across the planet and in space swung into action, capturing data that confirmed the Cow was real. And utterly unlike anything seen before, theories erupted faster than the explosion itself. One leading idea suggests we witnessed the birth of a black hole or neutron star in real time. When massive stars collapse, their cores typically vanish behind an opaque shroud of debris, leaving observers to piece together the aftermath. But the Cow might have been a rare, failed supernova, where a star massive enough to form a black hole instead implodes directly without the usual fireworks. In this scenario, the Cow's brief, intense glow could have been the black hole's accretion disk flaring to life, consuming stellar material in a feeding frenzy before settling into invisibility. Another possibility is even more dramatic, a tidal disruption event where a black hole shreds a passing star. Most known TDES occur when supermassive black holes rip apart sun-like stars, but the Cow's host galaxy lacks such a monster at its core. Instead, a smaller stellar mass black hole might have encountered a dense, compact object, perhaps a white dwarf, tearing it apart in a uniquely violent encounter. The resulting plasma jet pointed directly at Earth could explain the Cow's blinding X-ray emissions. Yet even these radical explanations don't account for everything. Spectra revealed the Cow expelled material at 10% the speed of light, far faster than typical supernova, and its chemical fingerprints were oddly devoid of hydrogen and helium, suggesting the progenitor star had already shed its outer layers before the detonation. Some researchers speculate we saw a magnetar being born, a neutron star with a magnetic field a quadrillion times stronger than Earth's, whose unimaginable forces powered the explosion. The Cow's legacy transcends any single theory. It represents a new class of cosmic transients, fast blue optical transients, or FBOTS, that challenge our definitions of stellar death. Traditional models assumed supernova and gamma-ray bursts covered all possibilities. Now, we're seeing the universe has stranger, faster ways to destroy stars, ones that leave little trace beyond a fleeting, brilliant scream of light. New telescopes like the Vera Rubin Observatory are scouring the skies for more of these enigmas. Each one could be a clue, not just about how stars die, but about the hidden physics governing the most extreme moments in the cosmos. Just when we thought we knew Proxima Centauri, the closest star to our Sun, it throws us another cosmic surprise. In 2020, astronomers announced the discovery of Proxima c, a frigid super-Earth orbiting this tiny red dwarf, adding another twist to the already puzzling system that hosts Proxima b, a potentially habitable world. But Proxima c isn't just another planet. Its very existence defies conventional wisdom, sitting in an orbit so wide and so cold. It shouldn't be there according to our best models of how planetary systems form. At roughly 7 times Earth's mass, Proxima c is a frozen giant, circling its star once every 5.2 Earth years at a distance about 1.5 times farther than Earth is from the Sun. That might not sound extreme until you remember Proxima Centauri is a dim, cool star, barely a tenth the Sun's mass. At that distance, Proxima c's surface hovers around -230 degrees Fahrenheit, making Pluto look balmy by comparison. Yet the real shock isn't its temperature, it's how it got there in the first place. Standard planet formation theories suggest worlds like this shouldn't exist around red dwarfs. These stars form from collapsing clouds of gas and dust, with planets coalescing in the dense inner disk. But Proxima c's orbit lies far beyond the expected snow line, the region where volatile compounds like water freeze, typically the birthplace of gas giants, not rocky super-Earths. For a planet this massive to form so far out, the protoplanetary disk around Proxima Centauri would have needed far more material than red dwarfs are thought to possess. That's led to wild alternative explanations, including the possibility Proxima c didn't form here at all, but was yanked outward by gravitational interactions with another star, or even kicked into place during a violent cosmic collision. The intrigue doesn't stop there. Proxima c's discovery came not from the usual transit method or radial velocity wobbles, but through a technique called astrometry, tracking the star's precise position over years, looking for the subtle gravitational tug of an unseen companion. This makes it a milestone in exoplanet detection, proving we can find worlds that don't play by the usual rules. Follow-up observations from the Very Large Telescope in Chile even hinted at a possible ring system or a shrouding haze of dust, adding layers to its mystery. But the most tantalizing question remains: could Proxima c have siblings? Its wide orbit leaves room for more planets lurking in the darkness, perhaps even within the habitable zone alongside Proxima b. And if tiny, faint stars like Proxima Centauri can host multiple worlds, some habitable, some bizarre outliers, it drastically increases the odds that life-friendly pockets are scattered throughout the galaxy. Upcoming telescopes like the Extremely Large Telescope, set to probe Proxima c's atmosphere in the 2030s, might finally unravel how this misfit planet came to be. Until then, it stands as a reminder, even the closest stars still guard secrets that force us to rethink everything. For centuries, alchemists dreamed of turning lead into gold, but it turns out the universe had its own secret recipe all along, one that required a violent dance of the cosmos' densest objects. On August 17, 2017, astronomers witnessed history: 2 neutron stars spiraling toward each other in a galaxy 130 million light-years away, culminating in an explosion so powerful it shook spacetime itself. Known as a kilonova, this collision didn't just light up the heavens, it forged an astronomical treasure trove of heavy elements, from gold and platinum to uranium, scattering them across the cosmos in a single, glittering burst. The discovery was a watershed moment, decades in the making. Scientists had long suspected neutron star mergers could synthesize these precious metals, but direct proof remained elusive. Then, in a stroke of cosmic luck, the Laser Interferometer Gravitational Wave Observatory LIGO caught the ripples of the star's death spiral gravitational waves whispering across the universe. Within seconds, telescopes around the world swiveled toward the source, capturing the event in every wavelength from gamma rays to radio waves. What they saw was staggering: a flare of light 1,000 times brighter than a typical nova, tinged with the unmistakable spectral fingerprints of rare Earth elements forming in real time. Here's how the magic happens. Neutron stars are the crushed cores of dead stars, so dense a teaspoon of their material weighs as much as a mountain. When 2 of them collide, the extreme pressures and temperatures reaching trillions of degrees rip apart their nuclei, unleashing a frenzy of nuclear reactions. Neutrons flood the environment, bombarding lighter atoms in a process called rapid neutron capture, or the R process. In seconds, elements like gold and platinum are born, their atomic nuclei ballooning as they greedily absorb neutrons before decaying into stable forms. The kilonova's aftermath revealed something even more astonishing. This single event likely produced hundreds of Earth masses worth of gold alone, along with other heavy metals. Suddenly, the origins of your wedding ring or smartphone circuitry took on cosmic significance, but the implications stretch far beyond bling. Kilonovae solve a long-standing mystery, where half the elements heavier than iron in the universe come from. Supernova can forge lighter, heavy elements, but the R process requires neutron-rich conditions only mergers provide. By studying the 1720 event's light curve and spectra, researchers calculated that such collisions might be frequent enough to seed galaxies with these crucial materials over billions of years. Even our solar system's gold deposits could trace back to a nearby kilonova that exploded before the sun was born, sprinkling its riches into the primordial cloud that birthed our planets. The discovery also opened a new era of multi-messenger astronomy, where gravitational waves and light work in tandem to reveal cosmic secrets. For the first time, scientists could correlate the chirp of colliding stars with the fireworks show that followed, peering into the heart of an explosion that would have been invisible just a decade prior. Future observatories like the Einstein telescope aim to detect these events even farther back in time, potentially uncovering the very first kilonovae that enriched the early universe with the elements needed for life. What's truly humbling is the scale of this alchemy. A single neutron-star collision might last mere seconds, but its legacy endures for eons. In the gold beneath our feet, the uranium powering reactors, even the iodine in our bodies. The universe doesn't need a philosopher's stone. It has something far more spectacular, the dying screams of stars echoing across the ages as they turn emptiness into treasure. There's a place in the universe so unsettlingly empty, it makes the deepest voids of space seem crowded by comparison, the Boötes void. Stretching 330 million light-years across, this cosmic desert contains just 60 known galaxies where models predict there should be thousands. To put that in perspective, if the Milky Way were placed in the Boötes void, our nearest galactic neighbors would be so distant, astronomers wouldn't have discovered them until the 1960s. This isn't just a gap in the cosmic web. It's a staggering anomaly that makes scientists question whether our understanding of the universe's structure is fundamentally flawed. What makes the Boötes void so baffling is its defiance of the standard model of galaxy formation. After the Big Bang, matter clumped together under gravity, creating filaments and clusters with vast voids between them, like froth in a bubble bath. But even the largest voids typically contain some galaxies strung along faint tendrils. The Boötes void, however, is too empty, as if something scooped out the galaxies and left behind a vacuum. One theory suggests it might be the result of multiple smaller voids merging over eons, amplifying the emptiness. Others propose more exotic explanations like quantum fluctuations in the early universe that left this region bizarrely underdeveloped. Then there's the wild card. Could the Boötes void be evidence of alien engineering on an unimaginable scale? The idea stems from the hypothetical Dyson sphere, a megastructure advanced civilizations might build to harness a star's energy. Some speculative theorists suggest an ultra-advanced society could expand such projects across galaxies, perhaps dismantling them for resources or creating vast, empty zones for reasons beyond our comprehension. While mainstream science dismisses this as science fiction, the sheer scale of the void forces us to reckon with how little we know. If natural processes can't fully explain it, what else might be at play? Recent surveys have added new wrinkles to the mystery. Deep field observations reveal that some of the void's sparse galaxies are oddly aligned, as if drawn into strings hinting at hidden gravitational forces or dark matter flows we can't yet map. Even stranger, a few of these galaxies show unusual star formation rates, as if their isolation triggered unique evolutionary paths. The more we study the void, the clearer it becomes. This isn't just an absence. It's a laboratory for testing the limits of cosmology, where the rules we take for granted might not apply. The Boötes void challenges us to think bigger about the universe's structure, the nature of emptiness, and even the possibility of phenomena we've yet to imagine. For now, it remains one of space's most profound puzzles, a silent enigma that reminds us, sometimes what's missing is just as important as what's there. Jupiter's icy moon, Europa, has long been one of the solar system's most tantalizing mysteries, a frozen world hiding a secret beneath its cracked, pale surface. But in 2013, the Hubble Space Telescope delivered a bombshell. Europa isn't just hiding an ocean, it's spraying it into space. Towering plumes of water vapor, some reaching over 100 miles high, were caught erupting from the moon's south pole like geysers from another world. This wasn't just a scientific curiosity, it was humanity's first direct glimpse of the liquid water lurking below, and with it the thrilling possibility that Europa's ocean might be closer and more accessible than we ever dreamed. The discovery hinged on Hubble's keen eye. By observing Europa as it passed in front of Jupiter, astronomers could study the moon's silhouette in ultraviolet light. What they saw was startling, faint, intermittent patches of absorption, as if something water vapor perhaps was blocking starlight around the moon's edges. Follow-up observations in 2016 confirmed it. These weren't random atmospheric wisps. They were concentrated jets erupting from the same region where thermal imaging had earlier revealed unexpected heat signatures, hints of friction from shifting ice or even hydrothermal vents on the ocean floor below. Suddenly, the pieces fit. Europa's subsurface ocean, kept liquid by Jupiter's gravitational flexing, was finding ways to vent its contents into space through cracks in the icy shell. What makes these plumes revolutionary isn't just their existence. It's what they represent, a shortcut to studying Europa's hidden ocean without drilling through miles of ice. Imagine a robotic spacecraft flying through one of these eruptions, sampling the water directly for organic molecules, salts, or even microbial life. The plumes could be cosmic elevators delivering treasures from the depths to our instruments, but there's a catch: they're frustratingly sporadic. Unlike Enceladus, Saturn's moon with its predictable geysers, Europa's eruptions seem capricious, flaring up and vanishing without warning. Some scientists speculate they're tied to tidal stresses, times when Europa's orbit brings it closest to Jupiter, flexing its icy crust like a stress ball and squeezing water through fissures. Others suggest underground volcanic activity might drive them, creating pockets of pressurized water that occasionally burst free. Enter the JUICE mission, the European Space Agency's audacious plan to crack Europa's code. Slated to arrive at Jupiter in 2031, the Jupiter Icy Moons Explorer won't just observe from afar. It's equipped with an arsenal of instruments designed to analyze plume chemistry, map subsurface ocean currents using magnetic fields, and even peer beneath the ice with radar. But the real game-changer might be its planned close flyby, a daring dash through a suspected plume where its mass spectrometer could taste the ejected water for amino acids or other biosignatures. The implications are staggering. If Europa's plumes carry even traces of organic material, it would suggest the moon's ocean is more than just water. It's a dynamic soup of chemistry, potentially ripe for life. And if JUICE finds evidence of hydrothermal vents on the seafloor, analogues to Earth's life nurturing black smokers, the case for Europa as a habitable world grows exponentially stronger. We might be looking at a place where life could arise independently of the sun, powered by Jupiter's gravity and the moon's own internal heat. Yet for all the excitement, Europa's plumes also pose riddles. Why do they erupt so unpredictably? Are they tapping into the global ocean or isolated subsurface lakes trapped between layers of ice? And most hauntingly, if life exists there, could it survive the journey into space only to be freeze-dried in the vacuum? Every new observation peels back another layer of this enigmatic moon, revealing not just answers but deeper questions. One thing's certain, Europa isn't just a frozen orb. It's a living, breathing world with secrets bursting forth for those brave enough to reach out and catch them. The universe is expanding, that much we've known for a century. But how fast it's growing, that's where things get messy. Right now, cosmologists are locked in a battle over one number, the Hubble constant, and the discrepancy between how we measure it has become so glaring, it's threatening to unravel our understanding of the cosmos. This isn't just a minor math error, it's a full-blown crisis that could force us to rewrite the laws of physics. On one side, we have the gold standard method, studying the cosmic microwave background, the afterglow of the Big Bang. By mapping its faint ripples with exquisite precision, Planck satellite scientists calculated the universe's expansion rate should be about 67 kilometers per second per megaparsec. On the other side, astronomers using pulsating stars and exploding supernova as cosmic yardsticks insist the number is closer to 73. At first glance, that 6-kilometer difference seems trivial until you realize these measurements are now precise enough that the gap can't be brushed off as experimental error. The universe appears to be expanding faster than our best models predict, and no one can quite explain why. This Hubble tension has sent theorists scrambling. Some propose dark energy, the mysterious force accelerating cosmic expansion, isn't constant after all, but growing stronger over time. Others speculate there might be an unknown particle, like a dark radiation, zipping through space and subtly altering the early universe's behavior. The wildest idea, that our universe collided with another bubble universe in the distant past, injecting extra energy that's now throwing off our calculations. Each hypothesis is more radical than the last, but that's the point when the data refuses to cooperate. Even fringe ideas get a seat at the table. What makes this crisis so profound is its stakes. If we've misjudged the Hubble constant, it means our entire cosmic timeline from the first seconds after the Big Bang to the fate of everything might be wrong. Distances to galaxies, the age of the universe, even the amount of dark matter could need recalibration. Future telescopes like the Nancy Grace Roman Space Telescope aim to settle the debate with new, ultra-precise measurements, but until then, the tension remains. It's a stark reminder that the universe doesn't owe us tidy answers, and sometimes the most fundamental truths are the ones that slip through our fingers. When a star explodes, it's supposed to leave behind a predictable graveyard of elements: iron, silicon, maybe some neon. But in the constellation Cassiopeia, the remnants of a supernova called Cassiopeia are telling a different story. Here, astronomers have found vast clouds of oxygen lingering like cosmic ghosts, defying everything we thought we knew about how stars die. These oxygen-rich pockets shouldn't exist, not in these quantities, not this intact. And their presence is forcing scientists to reconsider the violent final moments of stellar giants. The enigma starts with the star's death throes. When massive stars run out of fuel, their cores collapse, triggering a shockwave that blasts the outer layers into space. Standard models predict lighter elements like oxygen and carbon should be obliterated in the process, either fused into heavier metals or vaporized by the explosion's fury. Yet observations from telescopes like Chandra and Spitzer reveal Cassiopeia brimming with oxygen, enough to fill 1,000 solar systems concentrated in eerie, bubble-like structures. It's as if chunks of the star's interior were flung outward unscathed, preserved like cosmic time capsules. One leading theory suggests these oxygen pockets might be signatures of a failed explosion, a supernova that didn't quite succeed. In this scenario, the star's core collapses into a neutron star, but the shockwave stalls, unable to fully erupt. As the neutron star's intense magnetic field spins up, it might reignite the stalled shock, creating a secondary burst that launches isolated clumps of unburned material into space. These oxygen-rich bullets would then coast through the debris, untouched by the nucleosynthesis that forged heavier elements elsewhere in the remnant. Another possibility is even more exotic, a pulsational pair instability supernova. Stars between 120 and 240 times the Sun's mass might experience violent convulsions late in life, shedding enormous shells of oxygen in bursts before the final detonation. The remnants of these pre-explosion eruptions could survive the later cataclysm, explaining why Cassiopeia A's oxygen looks so pristine. If confirmed, this would mean the star didn't just die once, it suffered multiple near-death experiences before its grand finale. What makes this discovery so revolutionary isn't just the challenge to stellar models. Oxygen is the third most abundant element in the universe, crucial for water, rocks, and life itself. If supernova routinely spit out intact oxygen instead of destroying it, it could rewrite our understanding of how the building blocks of planets and people are scattered across the cosmos. Future telescopes like the James Webb Space Telescope will hunt for similar remnants, searching for patterns that might reveal whether Cassiopeia is a cosmic oddity or the rule we've been missing. One thing's certain, the universe's recycling program is far more nuanced than we ever imagined. Imagine looking at a map of the cosmos so vast it makes the Great Wall of Galaxies seem like a local landmark. Now picture a structure so enormous, it stretches across 1/15 of the entire observable universe, a nearly symmetrical curve of galaxies arcing through the constellation Boötes like a celestial rainbow. Astronomers call it the giant arc, and its sheer size isn't just impressive. It's impossible according to everything we thought we knew about how the universe organizes itself on the grandest scales. Discovered in 2021 by University of Central Lancashire researcher Alexia Lopez, the giant arc spans an unfathomable 3.3 billion light-years, comprising galaxies, galaxy clusters, and clouds of intergalactic gas strung together in a near-perfect crescent. What makes this structure so revolutionary isn't just its scale, it's that it blatantly violates the cosmological principle, a cornerstone of modern astronomy stating that, on large enough scales, the universe should look roughly the same in every direction. Matter ought to be distributed evenly, like sprinkles mixed into cake batter. Yet here's the giant arc, a glaring exception where galaxies align in a pattern so precise, the odds of it forming randomly are less than 1 in 20,000. The implications are staggering. If such megastructures are real, they could upend our understanding of cosmic evolution. One leading theory suggests the arc might be a fossilized imprint of the early universe, a relic from when spacetime itself was stretched and knotted by gravitational waves during cosmic inflation. Another, more radical idea proposes its evidence of exotic physics, like defects in the quantum fabric of reality left over from the Big Bang. Picture the universe as a cooling sheet of ice. As it crystallized, cracks might have formed, trapping pockets of matter into unnatural alignments. But the real controversy lies in the data. Some scientists argue the arc could be a statistical fluke, a trick of perspective where unrelated galaxies appear connected when viewed from Earth. Others counter that its redshift measurements, which track how fast the galaxies are moving away from us, reveal they're genuinely linked, drifting through space as a cohesive unit. The debate highlights a fundamental challenge in cosmology. When you're mapping structures larger than anything in human experience, how do you distinguish a true pattern from a cosmic mirage? Future telescopes like the European Space Agency's Euclid mission might settle the argument by mapping galaxy distributions in 3 dimensions, revealing whether the giant arc is a physical structure or a fleeting illusion. But if it's real, prepare for a paradigm shift. The universe might not be the smooth, homogeneous expanse we've assumed. Instead, it could be threaded with hidden scaffolds, vast, ancient blueprints we're only beginning to trace. And if one giant arc exists, who's to say there aren't others lurking in the darkness, waiting to rewrite cosmology once again? Saturn's moon Titan has always been a world of contradictions, a place where rivers carve valleys not with water, but liquid methane, where dunes rise taller than skyscrapers, made not of sand but frozen organic molecules. Yet, even among its many wonders, one phenomenon stands out as truly bizarre. A phantom patch of brightness that appears and vanishes in its methane seas like a cosmic sleight of hand. Astronomers call it the Magic Island, and its fleeting nature has sparked a detective story spanning years, with suspects ranging from crashing waves to chunks of alien icebergs. The mystery began in 2013 when NASA Cassini spacecraft trained its radar on Ligeia Mare, Titan's second-largest methane sea. In one series of images, a bright splotch roughly 100 square kilometers in size, about the area of Manhattan, materialized where none had been before. By the next flyby, it was gone. Then, in 2014, it reappeared, only to fade again like a whisper in the wind. This wasn't some camera glitch. The island was real, and it was defying every attempt to explain it. The leading theory: waves. On Earth, choppy seas reflect radar differently than calm waters, creating bright patches in satellite imagery. Titan's thick atmosphere and low gravity could allow methane waves to rise taller and last longer than terrestrial ones, especially during seasonal changes when wind speeds increase. But there's a problem. Titan's seas are usually eerily still, with surface ripples estimated to be mere millimeters high. For waves to create such a stark radar signature, they'd need to be monumental, churning with energy we've never observed. Then there's the bubbling hypothesis. Titan's frigid temperatures hovering around -290 degrees Fahrenheit allow nitrogen to dissolve in methane like carbonation in soda. If pockets of this nitrogen suddenly came out of solution, they could erupt as sprawling fizz fields, scattering radar signals in every direction. It's a compelling idea, except nobody's sure what would trigger such large-scale degassing. Seasonal warming, underground vents, the mechanisms remain as hazy as Titan's orange skies. But the wildest possibility is solid matter floating like interstellar debris. Titan's rivers carry organic compounds, complex chains of carbon and hydrogen washed down from its highlands. Some of these molecules might clump into porous, honeycomb-like chunks, buoyant enough to drift on methane's surface. Imagine a fleet of frozen sponges bobbing together until they sink, dissolve, or wash ashore. If true, these floating islands could be the closest thing to extraterrestrial continents we've ever found, albeit temporary ones. What makes this enigma so tantalizing isn't just the what, but the why now. Titan's seasons last 7 Earth years, and Cassini's observations coincided with the moon's northern summer solstice, a time of increased sunlight and atmospheric activity. Could the Magic Island be a seasonal spectacle, vanishing during methane winter, only to return when the sun warms the seas again? Without Cassini, which plunged into Saturn in 2017, we're left with only archival data to piece together the puzzle. Future missions like NASA's Dragonfly, a rotorcraft set to explore Titan's dunes in the 2034s, could settle the debate if it dares to venture toward the seas. Until then, the Magic Island remains one of the solar system's most captivating riddles, a reminder that even in our cosmic backyard, nature still has tricks up its sleeve. Imagine sending a pair of gloves into space, one to Beijing, the other to Vienna, and discovering that no matter how far apart they traveled, changing one instantly altered the other. This isn't magic, it's quantum entanglement, one of the most bewildering phenomena in physics, and in 2017, China's Misha satellite proved it works across staggering cosmic distances, shattering previous records and opening the door to a revolution in secure communication. The experiment was as elegant as it was mind-bending. Misha, named after an ancient Chinese philosopher, fired pairs of entangled photons particles linked in such a way that measuring one immediately determines the state of its partner, no matter the separation down to ground stations 1,200 kilometers apart. That's farther than the distance between New York and Miami, and triple the previous entanglement record. The photons weren't just connected. They defied classical physics by maintaining their spooky link even as they raced through Earth's turbulent atmosphere at the speed of light, confirming quantum mechanics' most radical prediction on a scale once deemed impossible. Why does this matter? Because entanglement isn't just a laboratory curiosity, it's the backbone of an unhackable quantum internet. Traditional encryption relies on math problems so complex they'd take centuries to solve, but quantum computers could crack them in minutes. Entanglement offers a solution. Any attempt to intercept or measure a quantum message disturbs its delicate state, alerting both sender and receiver to eavesdropping. Mischius proved this principle works globally, beaming entangled photons through open space while maintaining their cryptographic potential. Picture a future where financial transactions, military communications, and medical data are secured not by algorithms, but by the fundamental laws of physics themselves. Yet the implications stretch far beyond cybersecurity. Mischius's success hints at a universe far more interconnected than we imagined. If entanglement persists across continents, could it span star systems? Some theorists speculate that quantum networks might one day link satellites, lunar bases, and Mars colonies, creating an interplanetary web impervious to cosmic interference. Others ponder even wilder possibilities, like using entangled particles to test whether space-time itself emerges from quantum connections, a cornerstone of theories like holographic duality. The challenges remain immense. Maintaining entanglement over long distances requires exquisitely sensitive equipment, as photons can be absorbed or scattered by air molecules, dust, or even clouds. Mischius overcame this by using adaptive optics, mirrors that deform in real time to counteract atmospheric distortion. But scaling this for everyday use will demand breakthroughs in miniaturization and reliability. Then there's the dark night problem. Quantum signals can't penetrate daylight, forcing transmissions to occur in brief windows of darkness. Despite these hurdles, Mischius marked a turning point. It transformed quantum communication from tabletop experiments to a tangible, space-ready technology, proving that the bizarre rules governing particles in labs hold true across the vastness of our planet. And with missions like the European Space Agency's quantum cryptography telecommunication system already in development, the race to build a global quantum network is accelerating. What began as Einstein's spooky action at a distance might soon become the bedrock of a new era, one where the universe's strangest quirk becomes humanity's most powerful tool. There's something unsettling happening at the edges of our cosmic maps, a phenomenon so strange it threatens to redefine the boundaries of reality itself. Imagine watching hundreds of galaxy clusters, each weighing trillions of suns, all drifting in the same direction like leaves caught in a hidden current. This isn't just random motion. Astronomers call it the dark flow, and it suggests something immense, something beyond the observable universe, is pulling them toward the void. The discovery began with painstaking analysis of the cosmic microwave background, the afterglow of the Big Bang. By studying subtle temperature shifts in this ancient light, scientists noticed something bizarre. Galaxy clusters weren't just expanding with the universe, they were moving together at speeds exceeding 2 million miles per hour toward a single patch of sky near the constellations Centaurus and Hydra. What's chilling is that this motion shouldn't exist. The universe's expansion ought to scatter matter evenly, like raisins in rising bread dough. Yet here we are, watching as countless galaxies defy expectations, drawn toward an unseen horizon. The leading theory, our universe might be just one bubble in an infinite cosmic foam, beyond the limits of what we can observe, roughly 93 billion light-years in diameter. there could be other universes with vastly different physical laws, their gravitational influence leaking into ours. Picture standing in a foggy valley, feeling a breeze you can't see, knowing it must come from somewhere beyond the mist. That's the essence of dark flow, an invisible tug from a place we'll never see, hinting at realities we can only theorize. Skeptics argue it could be a statistical fluke or an artifact of incomplete data, but the evidence is mounting. When NASA Wilkinson Microwave Anisotropy Probe and later the Planck satellite both detected the same directional bias across thousands of clusters, the chances of coincidence dwindled to near zero. Even more compelling, the flow aligns with mysterious, large-scale voids in the cosmic web regions where galaxies are inexplicably scarce, as if something had cleared them out. Could these voids be the fingerprints of a collision between our universe and another in the distant past? The implications are staggering. If dark flow is real, it means the observable universe isn't the whole story. There's an outside, a beyond where forces we don't understand operate on scales we can't comprehend. It's like discovering your house has a secret door, one that leads not to another room but to an entirely different world. Future missions like the Euclid Space Telescope aim to map this motion in unprecedented detail, probing whether the flow strengthens or weakens with distance clues that could reveal whether we're dealing with a neighboring universe or something even stranger. For now, dark flow remains one of cosmology's greatest enigmas, a whisper from the edge of existence, reminding us that the universe we see might just be the tip of an unfathomable iceberg. And as we peer into that darkness, we're left to wonder what else is out there pulling the strings. Some planets don't just survive catastrophe, they emerge from it transformed into cosmic marvels. Take the world's orbiting pulsars, the lighthouses of the cosmos. These aren't just any planets, but survivors of stellar apocalypses, forged in fire and crystallized into what might be the universe's most exotic treasures. Their story begins with death. When a massive star explodes as a supernova, its core collapses into a pulsar, a spinning neutron star so dense, a teaspoon of its material weighs 1 billion tons. The blast should obliterate any nearby planets, yet against all odds, astronomers have found worlds clinging to these cosmic graves, their very existence defying expectations. The first pulsar planet, discovered in 1992 around the millisecond pulsar PSRB 1257+12, sent shockwaves through the scientific community. Not only did it exist, but its composition was unlike anything in our solar system. These planets are thought to be the skeletal remains of gas giants, their outer layers vaporized by the supernova, leaving behind ultra-dense cores rich in carbon. Under unimaginable pressures, that carbon crystallizes into structures that might resemble diamond, a core of gemstone the size of a planet, glittering in the harsh light of its undead star. How could something so fragile survive such violence? One theory suggests these planets formed after the supernova from the debris disk of shattered stars. As the pulsar's intense radiation and magnetic field whipped surrounding material into a frenzy, clumps of carbon and heavier elements could have coalesced into new worlds born from the ashes of the old. Another possibility is even more astonishing. These might be the scorched remnants of rocky planets whose silicate mantles were stripped away, leaving behind their diamond-studded hearts. The conditions are so extreme, they force carbon into forms we can't replicate on Earth-layered lattices that could conduct heat and electricity in ways that rewrite materials science. The pulsar's environment only adds to the strangeness. Bathed in lethal radiation and buffeted by stellar winds traveling near light speed, these planets endure conditions that would vaporize Earth in seconds. Yet they persist, locked in orbits so precise, their timings are measurable to the millisecond by the pulsar's lighthouse-like beams. Some even sport atmospheres not of oxygen or nitrogen, but vaporized metals like magnesium and iron, creating shimmering, metallic hazes that dance under the pulsar's glare. What truly captivates scientists isn't just their resilience, but what they represent: a glimpse into the incredible diversity of planetary formation. If diamonds can crystallize in the ruins of a star's destruction, what other wonders might lurk around these cosmic tombstones? Future telescopes could analyze the light filtering through their metallic atmospheres, hunting for spectral signatures of even more exotic materials. One thing's certain: the universe has a way of turning catastrophe into artistry, and pulsar planets are its masterpieces, cold, brilliant, and forged in the heart of darkness. Black holes come in two familiar sizes: stellar mass black holes, the collapsed cores of dead stars, and supermassive behemoths anchoring galaxies like our Milky Way Sagittarius A. But for decades, a glaring gap existed between them. Where were the middleweights? The missing link finally emerged in 2021, hidden in plain sight just 1,500 light-years away. Astronomers called it the unicorn, not just for its rarity, but because it lurked in the constellation Monoceros, the celestial unicorn. And this cosmic oddball wasn't just bridging a size gap, it was rewriting the rules of how black holes form and hide. What makes the unicorn so extraordinary is its mass, roughly 3 times that of our Sun, placing it squarely in the hypothetical intermediate mass range. Too small to be supermassive, yet too large to form from a typical stellar collapse, it defied classification. Most stellar black holes cap out around 15 solar masses, while supermassive ones start at millions. The unicorn occupied no man's land, challenging assumptions about whether black holes could even exist in this intermediate zone. Its discovery hinged on a clever workaround. Instead of observing the black hole directly, it's invisible. After all, researchers tracked the subtle wobble of a nearby red giant star. The star's motion betrayed an unseen companion's gravity, one too compact and heavy to be anything but a black hole. But the unicorn's true magic lies in how it's reshaping the hunt for hidden black holes. Traditional methods rely on spotting X-rays from their accretion disks, but the unicorn is quiet, devouring no nearby material. It's a ghost detectable only through gravitational influence. This suggests our galaxy could be teeming with similar dark wanderers, overlooked because they're not actively feeding. Some estimates now propose tens of thousands of such mid-sized black holes might be drifting undetected between the stars, each a silent testament to cosmic processes we've yet to understand. Theories about their origins range from the catastrophic to the bizarre. Perhaps they're primordial black holes forged in the chaos of the Big Bang itself. Or maybe they're the remnants of failed supernova, where massive stars collapse without the usual fireworks. The wildest idea: they could be the stitched-together remnants of smaller black holes merging in dense star clusters, growing stealthily over eons. Every possibility forces us to reconsider black hole evolution and raises new questions. If intermediate black holes are common, do they eventually merge into supermassive ones? Could they be the seeds from which galaxies grow? The unicorn's discovery is more than a cosmic curiosity. It's a roadmap. Future instruments like the Vera Rubin Observatory will scan for more of these gravitational whispers, potentially uncovering an entire population of missing link black holes. Each one could hold clues to the universe's most violent mergers, the formation of galaxies, and even the nature of dark matter. For now, the unicorn stands alone, a dark horse in the race to decode the cosmos' best-kept secrets. But if history tells us anything, it's that where there's one, there are bound to be more lurking in the shadows. The universe is supposed to be a place of chaos, galaxies scattered like grains of sand, obeying no grand pattern beyond the pull of gravity. Yet in 2024, astronomers stumbled upon something that defies this expectation. A colossal ring of galaxies so enormous it spans 1.3 billion light-years across, a structure so precise it looks like it was drawn by some cosmic hand. They call it the Big Ring, and its existence isn't just surprising, it's threatening to upend one of astronomy's most fundamental assumptions. This gargantuan formation, located 9.2 billion light-years away, isn't a physical loop of stars but a near-perfect alignment of galaxies, galaxy clusters, and quasars, all tracing a curve that covers 15 degrees of the night sky. To put that in perspective, if you held your fist at arm's length, the big ring would stretch the length of 3 fists side by side. What makes this so unsettling is the cosmological principle. The idea that on the largest scales, the universe should look roughly the same in every direction, with matter spread evenly like raisins in rising dough. The Big Ring's existence flies in the face of that. How does something this immense and symmetrical form in a cosmos that's supposed to be random? One leading theory points to Baryonian acoustic oscillations, sound waves that rippled through the infant universe during its first few 100,000 years. These waves, frozen in time as the cosmos expanded, could have created subtle overdensities where galaxies later clustered. But even this explanation struggles with the ring's scale and near-perfect circularity. The odds of such a structure forming naturally are astronomically low, leading some to propose even wilder origins. Enter cosmic strings, hypothetical defects in spacetime, theorized to have formed during the universe's earliest moments. These ultra-dense, thread-like structures, thinner than a proton but stretching across the cosmos, could have acted as gravitational scaffolds around which galaxies spiraled into rings. If true, the Big Ring might be the first tangible evidence of these exotic relics, a fossil from a time when reality itself was still cooling into existence. Yet not everyone's convinced. Skeptics argue the ring could be a trick of perspective, an illusion created by galaxies at different distances aligning by chance along our line of sight. But redshift measurements, which track how fast the galaxies are moving away from us, suggest they're genuinely linked, part of a coherent structure drifting through space together. The debate highlights a growing tension in cosmology. As our telescopes peer deeper, they're uncovering more of these impossible megastructures. The giant arc, the Hercules Corona Borealis Great Wall, each one chips away at the notion that the universe is homogeneous on large scales. What's at stake isn't just academic. If the Big Ring is real, it implies our universe might carry echoes of its birth in ways we've barely begun to decipher. Future telescopes like the European Space Agency's Euclid mission will map millions more galaxies, searching for similar patterns that could reveal whether this is a fluke or a fundamental feature of cosmic architecture. Until then, the Big Ring stands as a silent challenge, a cosmic question mark written in galaxies, daring us to rethink the very fabric of reality. Ceres, the largest object in the asteroid belt, was long dismissed as a frozen relic, a dull, cratered rock left over from the solar system's infancy. Then, in 2015, NASA's Dawn spacecraft revealed something extraordinary. Oumuamua, a solitary mountain rising 12,000 feet above the dwarf planet's surface. Its slopes not carved by impacts or tectonics, but built by something far more unexpected: ice volcanoes. This wasn't just a geological oddity. It was evidence that Ceres, a world barely 900 kilometers wide, might still be geologically alive, hiding reservoirs of briny water and pockets of heat beneath its icy shell. Oumuamua defies every expectation. Unlike Earth's lava-spewing volcanoes, this cryovolcano erupts a chilly slurry of water, salts, and mud, a process driven by internal heat that shouldn't exist in such a small, ancient body. The mountain's steep, smooth flanks bear no craters, suggesting it formed recently, perhaps within the last 200 million years, a blink in cosmic time. Even stranger, its summit cradles a distinctive depression, not from collapse, but from the final gasps of eruption as the icy magma chamber drained. Dawn's instruments detected salts like sodium carbonate lining its slopes, minerals that typically form in the presence of liquid water and heat. The conclusion was inescapable: Ceres hadn't just been active in the past. It might still be stirring today, Where does the heat come from? That's the real mystery. Unlike moons such as Europa or Enceladus, Ceres doesn't orbit a gas giant whose gravity could flex and warm its interior. Instead, scientists suspect radioactive decay or residual heat from its formation might keep deep reservoirs of brine liquid. Some theories even propose antifreeze compounds like ammonia lowering the freezing point of subsurface oceans, allowing sluggish convection currents to persist. The implications are profound. If a dwarf planet, a class of world once considered dead by default, can harbor internal heat and possibly liquid water, how many others might do the same? The Kuiper belt, packed with Ceres-like bodies, could be riddled with similar cryovolcanic wonders, but Oumuamua isn't alone. Dawn spotted dozens of other, older cryovolcanoes across Ceres, their features eroded but still recognizable. This suggests the dwarf planet has been episodically active for billions of years, with eruptions waxing and waning as heat sources fluctuate. The presence of organic compounds near some of these sites adds another layer of intrigue. On Earth, similar environments where water, heat, and organics mingle are hotbeds for microbial life. While no one's claiming Ceres hosts aliens, it's now firmly on the list of places where the ingredients for life might exist beyond Earth. Future missions could settle the question. Proposals like NASA's Ceres sample return aim to land near Oumuamua, drilling into its icy crust to analyze the chemistry up close. Others imagine penetrators or melt probes descending into suspected brine reservoirs, searching for signs of present-day activity. For now, Ceres stands as a testament to the solar system's hidden dynamism, proof that even the smallest worlds can harbor the most surprising secrets waiting for us to look closer. The idea that our sun might have a dark, murderous twin sounds like the plot of a cosmic horror story, but for decades some scientists seriously considered it. Meet Nemesis, the hypothetical stellar companion blamed for hurling deadly comets toward Earth in cycles of mass extinction. This theory emerged in the 1980s when paleontologists noticed an eerie pattern in the fossil record. Every 26 million years or so, life on our planet suffered catastrophic die-offs. The timing was too precise to ignore, and astronomers scrambled for an explanation. What if, they proposed, the sun wasn't alone? What if a small, dim star, a red dwarf, or even a brown dwarf orbited our solar system in a vast, elliptical loop, its gravitational tug disrupting the icy Oort cloud with each close pass, sending showers of comets spiraling inward to wreak havoc? Nemesis wasn't pure speculation. Binary star systems are common in the galaxy. In fact, most sun-like stars have companions. The hypothetical Nemesis would orbit at a distance of about 1.5 light-years, far enough to evade detection but close enough to periodically perturb the solar system's outer reaches. Early searchers focused on infrared surveys, hoping to spot the faint heat signature of a cool, distant object. Yet decades passed with no trace, no telltale blip in the data, no anomalous motion of nearby stars hinting at an unseen gravitational anchor. By the 2010s, advances in wide-field telescopes like WISE, the Wide Field Infrared Survey Explorer, had scanned the sky with unprecedented sensitivity, ruling out anything larger than a brown dwarf within vast swaths of space. So where does that leave the Nemesis hypothesis? Some researchers argue it's time to retire the idea entirely, pointing to flaws in the original extinction cycle data. The 26-million-year pattern, they note, might be a statistical artifact, a fluke of how we've dated ancient rock layers. Others counter that Nemesis could still exist, but as something even stranger, a stealthy black hole. Primordial black holes, hypothetical relics from the Big Bang, could theoretically lurk unseen, their gravity alone betraying their presence. A recent study even suggested that the peculiar orbits of some extreme trans-Neptunian objects might align in a way that hints at an undiscovered massive body, though not necessarily a star. Yet the most compelling twist comes from modern simulations. even if Nemesis isn't real, the solar system isn't immune to stellar interlopers. Around 70,000 years ago, a rogue star named Scolzes buzzed within just 52,000 astronomical units of the Sun, well within the Oort cloud. While too distant to trigger a comet storm, it proved that close encounters happen. Future Gaia mission data may reveal more of these flybys, painting a picture of a dynamic neighborhood where stars brush past far more often than we'd assumed. Whether Nemesis exists or not, the hunt has reshaped astronomy. It forced us to confront gaps in our celestial maps and spurred technology capable of spotting the faintest, coldest objects in the cosmic dark. And perhaps its greatest legacy is the reminder that our solar system, for all its seeming isolation, isn't an island. It's part of a vast, interconnected dance where even the unseen can leave scars. On a quiet August night in 1977, a radio telescope in Delaware picked up a signal so extraordinary, the astronomer who found it scrawled, "Wow." In red ink on the printout, a burst of noise 30 times louder than the cosmic background, lasting 72 seconds and never heard again. For decades, the WOW signal stood as the gold standard of potential extraterrestrial contact, a tantalizing blip that seemed too perfect to be natural. Yet new research suggests we might have been chasing shadows, not from distant stars but from something far closer to home. The mystery begins with the signal's unique signature. Detected by Ohio State University's Big Ear telescope, it hit precisely the frequency hydrogen absorbs and emits energy, 1,420 megahertz, a logical choice for aliens trying to get our attention. But the real shock was its intensity and brevity. Natural cosmic phenomena like pulsars or quasars don't pulse so brightly and vanish without a trace. The signal's narrow bandwidth also ruled out most terrestrial interference like satellites or aircraft. It seemed tailor-made to tease us, just long enough to be undeniable, just fleeting enough to defy explanation. Then came the comets. In 2016, astronomer Antonio Paris proposed a radical theory. What if the WOW signal wasn't alien at all, but the reflected radio chatter of our own civilization, bouncing off clouds of hydrogen surrounding two passing comets? At the time, these icy wanderers P/2008Y2 and 266P/Christensen hadn't been catalogued yet, placing them exactly where the signal originated. Comet nuclei shed hydrogen gas as they near the Sun, and solar radiation can ionize this envelope, creating temporary mirrors for stray radio waves. Earth's FM broadcasts ricocheting off these cosmic billboards might explain the bizarre one-off burst. The hypothesis sparked instant controversy. Critics pointed out that comets don't reflect radio waves efficiently enough to match the WOW signal's strength. Even more damning, follow-up observations failed to detect similar bursts when the comets returned. Yet the debate underscores a deeper truth. The line between natural and artificial signals is thinner than we thought. Modern SETI projects now actively track known comets, asteroids, and even space debris to rule out false positives, a lesson hard learned from 45 years of WOW signal speculation. What keeps the mystery alive is its timing. The signal appeared just once during Big Ear's years of operation, aligning with no known celestial event. If it was a comet reflection, why haven't we caught others? And why hasn't any subsequent scan of that patch of sky, including dedicated efforts by the Breakthrough Listen project, found a repeat? The original signal's frequency drift even matches what you'd expect from a transmitter fixed on a rotating planet, adding another layer of intrigue. The WOW signal endures not because it answers questions, but because it refuses to. It's a Rorschach test for our cosmic loneliness, proof that the universe can still startle us with moments of inexplicable clarity, then dissolve back into silence. Whether it was aliens, comets, or something we've yet to imagine, its legacy is undeniable. A 72-second reminder that sometimes the most profound discoveries aren't about what we find, but how long we keep searching. Empty space isn't really empty, at least not in the way we once thought. Even in the deepest cosmic voids where galaxies are scarce and darkness reigns supreme, the vacuum of space crackles with ghostly energy. These are quantum vacuum fluctuations, fleeting bursts of particles and antiparticles that pop into existence for mere fractions of a second before annihilating each other, like bubbles forming and bursting in a quantum foam. For decades, this phenomenon lived solely in theory, a bizarre consequence of quantum mechanics that seemed impossible to detect. Then, in a groundbreaking experiment, researchers found a way to measure these phantom particles, and in doing so, opened the door to technologies that could one day revolutionize space travel. The key lies in something called the Casimir effect. When two uncharged metal plates are placed incredibly close together in a vacuum, they're subtly pushed toward each other by an invisible force. This happens because the space between the plates is too narrow for certain virtual particles to form, while outside they continue flickering undisturbed. The resulting pressure differential creates a measurable attraction, direct proof that quantum fluctuations aren't just mathematical quirks, but tangible forces shaping reality. Experiments aboard the International Space Station have refined these measurements, removing Earth's atmospheric interference to reveal the vacuum's true behavior. What they've found is astonishing. The energy density of these fluctuations might be vast enough to warp spacetime itself. That revelation has sent shockwaves through theoretical physics, and not just because it hints at a deeper connection to dark energy, the mysterious force accelerating the universe's expansion. If we could somehow harness or manipulate these fluctuations, the implications for propulsion are staggering. Imagine a spacecraft that doesn't rely on traditional fuel, but instead taps into the vacuum's latent energy, effectively surfing on spacetime distortions. This isn't science fiction. NASA Eagleworks Laboratories has explored concepts like the Alcubierre warp drive, which would compress spacetime ahead of a ship and expand it behind, creating a bubble that moves faster than light without violating relativity. The catch: such a drive would require negative energy, a form of exotic matter that, as it turns out, might be hidden in the quantum vacuum's chaotic dance. Critics argue the energy requirements are insurmountable, at least with current technology. Stabilizing and extracting usable energy from virtual particles is like trying to catch smoke with your bare hands. Yet advances in metamaterials and quantum field manipulation are inching us closer. Some theorists propose using ultra-dense materials or high-frequency electromagnetic fields to amplify these effects, effectively pinning down virtual particles long enough to exploit their properties. Others suggest that dark energy itself could be the cumulative effect of quantum vacuum fluctuations on cosmological scales, a controversial idea that would unite two of physics' greatest mysteries. What's undeniable is how profoundly this discovery shifts our understanding of nothing. The void isn't passive, it's a seething, dynamic medium brimming with potential. Whether it leads to warp drives or simply deepens our grasp of the cosmos, one thing's clear: the universe's blank spaces are anything but empty. They're alive with possibility, whispering secrets we're only beginning to decode. At the frozen edges of our solar system, beyond the orbits of Neptune and Pluto, something massive is pulling space awry. A gravitational ghost bending the paths of distant objects into impossible alignments. Astronomers call this phantom planet 9, a hypothetical super-Earth lurking in the darkness, 10 times heavier than our world and 20 times farther from the Sun than Neptune. Its existence isn't just a hunch, it's the only explanation for the bizarre behavior of icy bodies in the Kuiper Belt, a region packed with dwarf planets and cometary fragments that should orbit randomly. Instead, they cluster in orbits angled sharply toward the same patch of sky, as if an unseen hand is herding them. The clues began stacking up in 2014 when astronomers Chad Trujillo and Scott Shepard noticed a peculiar pattern among extreme trans-Neptunian objects, bodies so distant they take thousands of years to complete a single orbit. These objects weren't just orbiting the Sun, their trajectories were tilted in eerily similar ways, with perihelia, their closest approach to the Sun, all bunched together. The odds of this happening naturally, less than 1 in 10,000. Enter Caltech's Konstantin Batygin and Mike Brown, who ran simulations showing these orbits could only stay aligned if something massive, a planet roughly 5 times Earth's mass, was shepherding them with its gravity. But Planet 9's influence might run even deeper. Some researchers suggest it could solve other solar system mysteries, like why the Sun's axis is tilted 6 degrees relative to the planets, or why certain objects like Sedna have orbits detached from Neptune's influence. Then there's the wildest twist: Planet 9 might not be native to our solar system at all. Simulations show it could be a rogue exoplanet captured by the Sun's gravity during the chaotic early days of the Milky Way. If true, it would mean our cosmic neighborhood harbors a frozen alien world hiding in plain sight. The hunt is now a high-stakes race, combing the sky with tools like the Subaru telescope in Hawaii and the Vera Rubin Observatory's upcoming legacy survey of space and time. The challenge: Planet 9's extreme distance means it reflects almost no sunlight, making it 1 billion times fainter than Jupiter. Even worse, its orbit could take up to 20,000 years to complete, leaving astronomers with just a sliver of the sky to search at any given time. Yet Batygin and Brown's latest calculations have narrowed the search area, predicting it might be lurking near the constellation Orion. Alternative theories have emerged. Perhaps a grapefruit-sized black hole or a swarm of smaller objects creates the same gravitational effects, but none fit the data as cleanly. What's undeniable is that something out there is warping the fabric of our solar system. Whether it's a lost super-Earth, a primordial interloper, or something even stranger, the discovery would rewrite our understanding of the Sun's domain. And until we find it, Planet 9 remains the ultimate cosmic detective story, a puzzle written in gravity, waiting for its final piece. From Oumuamua's interstellar enigma to the quantum whispers of empty space itself, these 30 discoveries don't just add footnotes to science, they tear up entire chapters and demand we start fresh. Each one is a crack in the foundation of what we thought we knew, revealing a universe far stranger, more dynamic, and more mysterious than textbooks ever dared suggest. Ancient water bursting from the moon's sun-baked surface, galaxies aligning into rings larger than logic allows, even the unsettling possibility that Venus's toxic clouds might hide life playing by rules we don't yet understand. These aren't just updates. They're revolutions. Consider the ripple effects. The detection of phosphine on Venus forces us to redefine the very boundaries of habitability. The giant arc and Boötes void challenge cosmology's core principle that the universe should look uniform at scale. And the revelation that black holes might not be singularities at all, but tangled quantum fuzzballs, could rewrite how we think about space-time itself. These discoveries don't exist in isolation. They're threads in a larger tapestry, hinting at cosmic truths we're only beginning to grasp. What unites them all is their audacity, the way they force us to confront how little we truly know. For every answer, they offer 10 new questions. Could pulsar planets be the galaxy's diamond factories? Is dark flow a tug from another universe? The more we learn, the clearer it becomes. The cosmos thrives on the unexpected, and our assumptions are its favorite targets. This isn't just science evolving its humanity, waking up to a universe that's alive with possibility, where even the emptiness of space crackles with potential. And the most thrilling part, this is just the beginning. With telescopes like JWST and missions like Dragonfly pushing further every day, who knows what paradigm-shattering revelation waits just over the horizon. Now it's your turn. Which of these discoveries left you awestruck? The oceans of Europa, the haunting mystery of the WOW signal. Drop your thoughts below, and if you're hungry for more cosmic curveballs, hit subscribe. The universe isn't done surprising us yet.